Pulse Width Modulation signal generation using STM32F103C8T6 Blue Pill Development Kit. Hi everyone, my name is Dr. Konark Sharma. In this lecture, we will learn a step-by-step approach to pulse width modulation signal generation for a motoring application using an ARM-based STM32F103C8T6 microcontroller on a Blue Pill development kit from Garvit Sharma and Urvashi Shrivastava. Upon completion of this lecture, learners will be able to understand how to use STM32 CubeIDE to program the STM32 microcontroller for pulse width modulation signal generation for a motoring application using STM32F103C8T6 Blue Pill development kit. So let's get it started.
KONARK'S research, subscribe now.
Welcome. In this video, we are setting up PWM pulse width modulation signal generation using STM32 Blue Pill. The board is connected and ready and powered through USB cable. We begin by opening STM32 CubeIDE, either creating a new project or opening an existing one. Here, we have unzip our program files, which is being connected to HTTP server. Pulse width modulation generation using STM32 with an emphasis on how circuit is connected, especially when PWM output is used to control a DC motor or a servo motor via drivers like L298N or directly via transistor. Here we have initialized up STM32 target selector. Now we are going to select our microcontroller, which is STM32 F103C8T6 microcontroller, which is the heart of Blue Pill board. This board, Blue Pill board, is a popular microcontroller development board known for its low cost and ARM Cortex-M3 power and versatile input-output. We are going to name our project as Blue Pill _PWM example. We'll select our targeted language, which is C++. We'll load our IOC in which our generated code will be coded. We'll render our user interface and we'll wait until our program creation happens. We'll wait for its completion. Blue Pill is a nickname for a compact development board built around STM32F103C8T6 microcontroller, a part of STM Microelectronics STM32 family. Its core is ARM Cortex-M3 32-bit. Clock speed up to 72 MHz. Now we have Pinout configuration tab. We configure one of the timer pins of PWM output. For example, we choose pin PA8, which maps to timer 1 channel 1. The moment it's assigned, CubeIDE automatically enables the timer peripherals. We are going to find our clock pulse as 72 MHz. We have selected our SYS as serial wire and system tick as a timer base. We can dive into timer 1 setting. Under the configuration tab, we switch the mode to PWM generation channel 1. Here we define timer's prescaler and auto reload value to set the frequency and duty cycle. After setting up a prescaler that divides our clock to our desired timing, then we enter a pulse value, which is 72 MHz, that controls the duty cycle of our PWM waveform. We are going to select TIM4 mode. We'll enable our internal clock, and then for the channel 4, we'll select PWM generation for channel 4. PWM pulse width modulation in STM32 is handled by TIM, which is timer peripherals. Each timer has channels connected to specific GPIO pins. For example, TIM1 channel 1 is connected to PA8. Here we have used TIM3 channel 4 to PB1. Our device configuration tool is updating our code. These pins are used for advanced control. Now we have a main.c file. With everything configured, we click Save and generate initialize code. STM32 CubeIDE now prepares all required HAL function for us. Inside the main.c file, you will find the key function HAL_TIM_PWM start. This line initiates PWM output on the selected channels. Here we are going to write HAL_TIM_PWM_start, which will start PWM on channel 4, which we have used in our program. It will use to initialize TIM1 with PWM settings. We are going to write the channel number and TIM. The channel number we used is channel 4. Now we are going to write the next line, which is HAL_GPIO_write pin. We are going to configure the GPIO pin connected to the TIM channel. We have a while loop. But before, we'll see that pin 8 has been configured by TIM pin 1. We'll also use HAL GPIO write pin GPIO pin, which is pin number 5, for the pin state, that the pin state will be 0. Now we are going to write a program for next line of HAL delay of 1000 milliseconds. Inside the while loop, we are going to write about. In this, we are going to use init32_t duty cycle. This declares an assigned 32-bit integer variable to store PWM duty cycle value. Initially initialized, likely start at 0 by default if global, or needs initialization if local. HAL GPIO_toggle pin GPIO-B GPIO_pin 8. Toggle state of pin PB8, which is an PWM pin. If it was high, it becomes low. If it is low, it becomes high. It could be used for debugging, triggering an LED, or making a waveform change on the oscilloscope. At HAL_GPIO toggle pin GPIO-B GPIO pin 5. We use PB5 for the triggering of an high to low with the toggle state of pin PB5 from high to low, or vice versa. We have a while loop of duty cycle less than 65535. This keeps increasing the duty cycle from current value, likely 0, until the max, which is 65535, which is a 16-bit maximum limit. We use TIMCRR4 is equals to duty cycle. This set PWM compare register CRR4 for timer 4 and channel 4. This defines how long the PWM output stays high in one period. You are gradually increasing the duty cycle. Duty cycle is equals to 100. Increment of duty cycle by 100 each time control the smoothness and speed of transition. HAL delay will wait 5 milliseconds between each duty cycle step for the smooth transition over time, which is approximately 327 steps into 5, which is 1.6 seconds for full RAM. In the second loop, which is while duty cycle less than 0, the loop runs in reverse, gradually decreasing the duty cycle back to 0. TIM4 CRR4 duty cycle updates the duty cycle again, and this keeps decreasing. Duty cycle minus equals to 100. This subtracts 100 from the current duty cycle to move to forward towards 0. HAL delay 5. Still delays 5 milliseconds gives smooth fading out or low speed down. This entire code toggles between two GPIO pins and gradually increase PWM duty cycles to full and then decrease back to its 0. This creates a fade in and fade out effects for a motor of PWM signal generation, which is controlled by PWM output on TIM4 channel 4. Now we have changed our HAL delay to 50 instead of 5. We'll wait until our code debugs. We see that some already made custom made code is there. We have deleted and we have write our whole code about it. In the side by side, we can see the tire of the motor connected, DC motor connected to our STM32 keeps moving by Pulse Width Modulation, and it will decrease to 0. Since we have edited our delay to 50, we'll see that it has decreased to 0 speed. First it increases the speed and then decreases back to 0. Thank you.
Finally, we would like to cooperate with you according to the best of our knowledge. Keep your feedback and suggestions coming. They help us to provide you quality work that resonates with your needs and requirements. Thanks much for sharing your kind suggestions. Keep healthy, keep learning, and keep growing.
KONARK'S Research. Subscribe now.